Welcome to oligosaccharide analysis using high-performance anion-exchange chromatography with Pulsed Amperometric Detection. I'm Tamlin Oliver, Managing Editor of Genetic Engineering and Biotechnology News, and I'll be the moderator for this webinar. This webinar, as you have probably already guessed, is all about HPAE-PAD, a well-established technique for carbohydrate analysis. Today we will focus on the application of this tried-and-true technique to oligosaccharide analysis. Our speaker, Jeff Rohr, Director of Applications Development, Dionex Products, Thermo Fisher Scientific, knows the technique inside and out and will share his expertise and best practices. He will also discuss glycoprotein applications, compare and contrast techniques, and answer your questions at the end of his presentation. Jeff will answer as many questions as time allows. You can submit a question at any time during his presentation by simply typing your question into the Ask a Question box and hitting Submit. All right, Jeff, we're ready for you to get started.
Thank you, Tamlin, and thank everybody else that's on the line here for taking the time out of their busy days to attend our webinar today. As Tamlin's already read the title, I just want to emphasize that although my title just says oligosaccharide analysis, I'm going to be specifically focusing on oligosaccharide analysis of glycoproteins. And on the next slide, you'll see my agenda, which in the first part, I'll give an introduction to what HPAE-PAD is. I will follow that with a discussion of how HPAE-PAD has been applied for carbohydrate analysis, and then get a little bit more specific and talk about the fundamentals of its application to oligosaccharides, and then specifically to glycoproteins, including the sample preparation techniques you use to get your samples ready to do HPAE-PAD of glycoproteins oligosaccharides. And then finally, I'll compare HPAE-PAD to other techniques for oligosaccharide analysis of glycoprotein oligosaccharides, and also talk about some other topics related to HPAE-PAD and oligosaccharide analysis from glycoproteins. And then I'll close with a few conclusions. So HPAE-PAD is just an acronym for High Performance Anion-Exchange Chromatography with Pulsed Amperometric Detection. So in this case, our separation portion of our chromatography is high performance anion exchange, and our detection portion is pulsed amperometric detection. Originally, this technique was referred to as high pH anion exchange chromatography with pulsed amperometric detection. As you'll see, the reason for that is pretty much all the separations occur at high pH, but there are some separations, which I won't discuss today, that actually occur more at neutral pH. Before I get started, I'll say that this is a well-established technique, as Tamlin mentioned in the intro. It was first described in the early 1980s, so about 30 years ago. There was a publication in 1983 showed how it could be used for carbohydrate analysis. But it really didn't catch on until it was first applied to glycoproteins in 1986 and 87. There was a couple of publications showing that it could be used specifically for oligosaccharide analysis from glycoproteins, and that sparked a lot of interest in the field. To date, there's well over 1,000 peer-reviewed publications that use this technique, and the technique is greater than 10 United States Pharmacopoeia official monographs. Some of you might remember the heparin problem of a few years back. They updated their monograph after that problem to contain a method that uses HPAE-PAD to determine impurities. So this is one example. There's also examples of aminoglycoside analysis, things like amikacin, kanamycin B, where HPAE-PAD is used as the main analysis technique for determining the quality of those pharmaceuticals. It's also been mentioned in at least one FDA points to consider document for recombinant glycoprotein characterization. The one document that I'm aware of most recently is in characterizing monoclonal antibodies for human use. Now, let's get down to the basics of what HPAE-PAD is, and we'll first start with the high-performance anion exchange chromatography portion. Now, carbohydrates, we usually think of them as neutral molecules, molecules that don't have a charge at neutral pH, so we don't think about separating them with anion-exchange chromatography. But carbohydrates can become oxyanions at high pH, so pH is greater than 12, because they have acidities, their pKa's, are in the 12 to 13 range. So this is why the technique was originally referred to as high pH, because for the most part, you're getting the pH high enough to make oxyanions. To get those pH high enough, therefore, we require hydroxide eluents, something like sodium hydroxide, that will make the carbohydrate an anion, so then we can do anion-exchange chromatography. Now, as we'll talk about in a bit, because we're using hydroxide eluents, that puts some specific demands on our liquid chromatography system. Now, if our carbohydrate is charged, so some carbohydrates are charged. A sialic acid has a negative charge. If it has a negative charge already, then we're going to need acetate in addition to that hydroxide as a strong eluent or mobile phase. That's going to be added to our hydroxide to elute the carbohydrate. Now, I should also have included if the carbohydrate is large. So it can be large and not have charge groups, and that'll cause enough binding to the column at high pH that we're going to need a stronger eluent like acetate. Now let's look at the PAD side of things, or Pulsed Amperometric Detection. So in this case, our carbohydrate, it's now been made an anion, is eluted from the column, and now it's detected on a gold working electrode. So that's a noble metal electrode, and it turns out that detection also requires high pH. For a carbohydrate to be detected on a gold metal electrode with applied potential, we need high pH. Well, that's a perfect marriage to the separation where we're using a high pH mobile phase. In fact, if we don't have a high pH mobile phase for the separation, we have to add high pH afterwards, but that's a very rare situation. Now, PAD itself is applying a series of potentials, what we call a waveform, to that working electrode, where the carbohydrate is detected at just one of those potentials. The other potentials are used to clean the electrode in situ and then get it ready for the next round of detection. Now, this all occurs pretty rapidly. We call this series of potentials a waveform, and our frequency is typically something like 2 hertz or 2 cycles per second. So that's a great frequency for doing liquid chromatography. Now, this shows an example of monosaccharide analysis to show the principles of HPAE-PAD. So, first of all, we're using a high-performance anion-exchange column, in this case, the CarboPac PA20 column. Now, I'm going to talk a little about the CarboPac column constructions and how that's important a bit later. But suffice it to say, this is a high-performance anion-exchange column. And here we're looking at the separation of 6 monosaccharides, fucose, the 2 amino sugars, galactosamine, glucosamine, and then 3 what we call neutral sugars of galactose, glucose, and mannose. You'll see they're all well separated, and you see our mobile phase, or our eluent, is 10 millimolar sodium hydroxide. So there it shows our high pH mobile phase. Now, in our detection, we see on the y-axis is nanocoulombs, or charge, because when we integrate the current that is generated by oxidizing those carbohydrates, that gives us charge. So these are well separated. You'll see there's 100 picomoles of each, good sensitivity. We could go down to less than a single-digit picomole if we need to. I'll show you some more sensitive work in a little bit. But this shows your general principle. We didn't have to derivatize the carbohydrate. It's detected. We're separating on a high-performance anion-exchange column with a sodium hydroxide at high pH mobile phase. So what's required to do HPAE-PAD? I said that this fact that we have a high pH mobile phase presents special demands to our chromatography system. Well, we require a non-metallic, and we also require a high-pressure liquid chromatography system. This is something that Thermo Fisher Scientific has specialized over a number of years of making these types of systems specifically for HPAE-PAD. We also need high-quality deionized water. We can't have impurities in our water. We need an autosampler that's capable of low microliter volume injections because for a glycoprotein analysis, we're only analyzing small amounts of sample. And we need a high-performance anion-exchange column that's actually designed for carbohydrate analysis. And I'm going to talk about those columns in just a short while. And then finally, we need an electrochemical detector and a cell capable of executing the waveforms we use for that carbohydrate analysis. Again, this is an area that Thermo Fisher Scientific pioneered 30 years ago and is continuously improved upon. Now, why is HPAE-PAD an established technique? I've told you that it's been around for 30 years. It's in over 1,000 publications. How did that come about? Well, first, as I mentioned earlier, there's no sample derivatization required for either separation or detection, so it's a direct analysis method. This is great because you can see exactly what you're looking for. As I mentioned also, it's a very sensitive detection technique. You can look at picomole quantities of carbohydrates. Again, high-resolution separations. When this technique first came out, there were separations that had never been seen before by any other technique. High capacity. The columns allow you to determine a small amount of carbohydrate in the presence of a large amounts of others. So you can look for, in some cases, impurities, but you can also look for, more likely, low abundance structures of carbohydrates. And for applications outside of glycoprotein analysis, there are many other cases where we're in a high abundance of one sugar, we're looking for a small amount of another sugar, in the case where that small amount is a critical component. We're not going to talk about any of that today, but this is, again, one of the things that made this technique well established. And finally, it's a one technique you're able to do a wide range of carbohydrate analysis. You can do monosaccharides, sialic acids, glycoproteins. I'll cover this more toward the end of the presentation. And then this is something we'll specifically cover during the presentation. With one separation, you can look at both products and substrates. And that includes labeled products. When people actually label sugars, you could actually look at the substrates and products. And I'll show you how that's important. So HPAE-PAD is a very popular technique for glycoprotein analysis, and there's many applications in glycobiology. These are some of the ones I've specifically mentioned. I showed you monosaccharide compositional analysis. Well, I showed you a standard. That's the kind of standard you would use during analysis of monosaccharides from a glycoprotein. Also, sialic acid analysis, looking at N-acetylneurominic acid and N-glycolyl-neurominic acid. Mannose-6-phosphate analysis. There's a number of recombinant products that are made for enzyme replacement therapies that have mannose-6-phosphate. This technique can do that analysis. And then finally, what we're going to talk about today is glycoprotein oligosaccharide analysis. So again, all four of these analyses can be done on the same system, and actually one column if you so choose. Usually we have specialized columns for each of those applications, but one column can do all those applications. So let's look at some general conditions for glycoprotein oligosaccharide analysis. Now, today we would start with a CarboPac PA200 column, and I'm going to describe that column on the next slide. So that's our best column for oligosaccharide analysis. But we've had a number of columns, two other columns specifically in the past, and we still sell both these columns, the CarboPac PA100 and the CarboPac PA1, both very fine columns, and I'll show you the difference in those columns and the 200 in the coming slides. But we'd start with one of those columns for the analysis. Now, in this case, our eluent would be probably 100 millimolar sodium hydroxide. We might use a little less or a little bit more sodium hydroxide, but generally 100 millimolar. So this is a lot higher than that monosaccharide analysis I showed you, which was 10 millimolar. But this makes sure all our carbohydrates are ionized, and it makes sure our detection is in an optimal range. And then, as I mentioned if our carbohydrate is charged or if it's large, I'm going to need a stronger mobile phase. In this case, I'm using sodium acetate. And usually that's delivered in a gradient. I have here as high as 500 millimolar. For glycoprotein analysis, we're generally in the 200 to 300 millimolar range. And then we see our flow rates, pretty typical flow rates for liquid chromatography, and again, our detections by PAD. For more details on that detection, you can see our technical note 21. Samples are generally dissolved in water. They can be dissolved in other things too, but water's typical. And then, as it mentioned in the bottom there, these columns are available in much larger formats for preparative and semi-preparative applications. So the way we make these columns, and I should point out that not only our system has to be tolerant of the high pH, the column has to be tolerant of the high pH. So a silica-based column you use for HPLC you can't use for this technique because it would simply dissolve in that mobile phase of sodium hydroxide. So we take as a solid core of styrene divinyl benzene and ethylvinyl benzene. That is 0 to 14 pH compatible. From there, we cook that in hot sulfuric acid, and that gives us the sulfated groups around the core. So that now it's basically a cation exchanger, which is not what we want. What we want to do is make an anion exchanger. So to do that, we add small beads. That's those beads to the right. They have quaternary ammonium groups, so the anion exchangers, and they bind electrostatically to that core bead that's been surface sulfonated. What this does is gives a short diffusion path length. This gives us short diffusion path length so that we get good high resolution separations. And that's basically how most of our CarboPac family of columns are prepared, and specifically the ones I'm talking about today, the 200, the 100, and the 1 are all prepared in the same manner. And really where the variation is in the way we make the core, either its size or the way we cross-link it, and a little bit on how we do the surface chemistry to do the anion exchange. So let's look at a separation. This is really our hallmark separation of glycoprotein oligosaccharide analysis. It's the very common glycoprotein bovine fetuin, and here we're looking at the N-linked or the asparagine-linked oligosaccharides that have been released previously from the glycoprotein, and then they've been reduced to make them oligosaccharide alditols. Now, here we're using the CarboPac PA100 column with its guard, and again, we're running an acetate gradient. What I want to call your attention to are specifically peaks 3 or 4, are major peaks. Before HPAE-PAD came along, these two peaks had never been separated. And what these peaks are, we'll see in the next slide, are these two structures. So these are isobaric structures, meaning they have the same molecular weight. The only difference is in the sialic acid linkage on the top left-hand corner of each structure. So you'll notice on the top structure, that sialic acid or N-acetylneuramidic acid is linked alpha-2,6, and in the bottom, that's linked alpha-2,3. So these are what we call linkage isomers, and we are able to separate both those with this column, and we are also able to separate those with the PA1 column. So if we go back to that slide before, you also note peaks 1 and 2 and 5 and 6. Those peaks have the same linkage difference. They're just a different structure. The peaks 1 and 2 are disialylated, meaning they're -2 charge. They have 2 sialic acids. Peaks 3 or 4 are trisialylated, and peaks 5 and 6 are tetrasialylated, means they have 4 sialic acids. And again, these only differ by isomers. And in fact, almost all these peaks along here along the separation have some kind of isomeric difference. We're going to look a little closer at all those structures a bit later in the presentation. So if we now look at that same sample, but now separated on the CarboPac PA200 column, you'll note that the peaks are now, those peaks that were almost baseline resolved are baseline resolved here. We're also seeing a lot more detail in the smaller peaks. Again, this is the biggest difference in the CarboPac PA200 versus the 100 is that we're working with a smaller bead size. So, and like all chromatography, that gives us the benefit of higher resolution. So we get much better resolution here. And again, this is the column we would start with today if we were designing an oligosaccharide separation from glycoproteins. So let's look at what it takes to do HPAE-PAD glycoprotein oligosaccharide analysis. So first, we need to release the oligosaccharide from the glycoprotein. Now, for N-linked or asparagine-linked oligosaccharide, the most common way of doing that is using an enzyme called PNGase and amidase. And what that does is, as I'll show you in a bit, is cleaves the oligosaccharide straight from the asparagine of the glycoprotein. For O-linked or serine-threonine-linked oligosaccharides, in this case we use a chemical technique called reductive beta-elimination, which I'm going to describe in a bit. In that case, we're actually putting the oligosaccharides in sodium hydroxide in the presence of a reducing agent, namely sodium borohydride. Now, some of the samples from those two preparations can actually be directly injected into an HPAE-PAD system. So this way we can save a lot on sample preparation. So let's look first at PNGase digestion. These are some general conditions for PNGase that can be used to put in prior to HPAE-PAD. As my final note there on this slide, we have much more details on this in application note 176. But essentially, we put the glycoprotein into a sodium phosphate buffer. There are other buffers that have been used. Put a little EDTA, some detergent in there, and then add the PNGase. For some proteins like IgGs, that's all we need for release. Now, for other proteins, you need a little bit more aggressive conditions, namely adding a reductant in beta-mercaptoethanol and also having a detergent present like SDS. And basically that should say 50 microliters, not 50 milliliters, but we generally inject something less than 50 microliter quantity. For the PA200, we're really generally in the 5 to 10 microliter injection. If we need to have BMA and SDS there, we can remove those by either drying for the BME, or we can also do cold ethanol precipitation to remove the SDS. So this is what happens with PNGase. We can see to the right there that the PNGase, as I've described before, cleaves between the N-acetylglucosamine of the N-linked oligosaccharide and the asparagine. Now, that's one way of doing this analysis, and I said the most common way, but there are also some endoglycosidases, such as EndoF2 or EndoH, and they actually cleave between the chitobias unit or those two N-acetylglucosamines, and those have also been used to prepare samples for glycoprotein oligosaccharide analysis for HPAE-PAD and, of course, many other techniques. Now, here's some general conditions for beta-elimination. Beta-elimination is a technique first described, I believe, in the 50s and by Carlson. But these are some conditions that were specifically used with HPAE-PAD in a paper by Anderson back about 20 years ago in Glycobiology. And as you see there, we're putting, as I mentioned before, we're putting the oligosaccharide, or the glycoprotein, in sodium borohydride with sodium hydroxide present, or really sodium hydroxide with sodium borohydride present is the better way to think about that. And we end up having to clean up the sample some. In this case, we've desalted with Biogel P2. There are other ways of cleanup, but generally the sample's cleaned up before it is then analyzed by HPAE-PAD or another technique. So let's look at some separations of glycoproteins and looking at low amounts to basically look at our sensitivity. So in this case, we've just taken our CarboPac PA200 column, and we're analyzing PNGase F digestions of the protein human transferrin isolated from human serum. So human transferrin is known to have mostly mono and disialylated. That means single and double sialic acid oligosaccharides. The top separation is designed to do both resolve neutral oligosaccharides in the first 30 or 40 minutes there, and then dissolve resolve the mono and disialylate and the other charged oligosaccharides. So this is what I would call a general screening analysis. Whereas the separation in the bottom panel is actually just designed to try to look at the charged oligosaccharides. So we use this as a model for analyzing low amounts of prostate-specific antigen, which I'll show you in the next slide. So this is part of a study we did it was an ABRF collaborative study looking at PSA glycosylation, which there's a lot of at the time, certainly there, and I think even today, there's still some question about the glycosylation, how much there is, what's there. This is a study mostly done with mass spectrometry, but we got the samples and applied HPAE-PAD to the analysis. So as we see, this is the total screening separation I described in the top panel of the last slide. And so I've blown up peaks this portion of the separation at where you see the dotted lines to show the neutral oligosaccharides. The black trace there is just the PNGase F blank. The blue trace is the PNGase F digestion of the PSA. You'll notice that there's only 1 microgram injected there, and we're seeing those particular neutral oligosaccharides, which I will describe in a bit. But suffice to say, there's not a lot of material there. If from 1 microgram of glycoprotein, that would translate to picomole quantities of the oligosaccharide. And then we see that there are mono and disialylate oligosaccharides in that portion of the separation that's at the end there. Now, if we take a little bit more, we can take a little bit greater detail looking at those charged oligosaccharides. So this is, remember, the bottom panel 2 slides back where I showed just a separation of the charged oligosaccharides. Here we see that here panel A, or chromatogram A, is just neutral oligosaccharide standard. So it shows you that they all elute in the front. But that's not what we're concentrating on here. What we want to look at is the mono and disialylate oligosaccharides. So sample B is 1 microgram of the PSA glycans. And then sample C is our model protein here, transferrin, so we know about where the mono and disialylated elute. So in this case, we can see there are different structures than what we would have in transferrin, but it is revealing to us that we have mono and disialylated oligosaccharides, and that's pretty much what the other techniques showed too. We also showed some charged oligosaccharides that aren't sialylated. As I'll show you, can treat our sample with an enzyme, neuraminidase, to remove the sialic acid, and we still had some charged oligosaccharides. One other of the mass spec techniques was able to pick that up too. Now, all the details of our work in this collaborative study can be found in application note 1050 or application note 1050. So I mentioned briefly using neuraminidase. One of the powers of HPAE-PAD, again, is that you can see both products and substrates, and you can use those while you're profiling oligosaccharides. So let's first talk about profiling, and then we'll talk about how you can use exoglycosidases like neuraminidase to assist in the identification of structures. So this is a rather old slide, but what it shows is an example of profiling using HPAE-PAD. So these are 3 different samples. The top sample A is a PNGase F digest of human polyclonal IgG. So you can buy human polyclonal IgG from a number of different vendors, treat it with PNGase F, and look at the oligosaccharides. Sample B is a monoclonal antibody that's expressed in mouse cells, so it's a murine monoclonal. And then sample C is another IgG. In this case, it's a humanized monoclonal. It's been expressed in Chinese hamster ovary cells. So you can see that while there are some of the same structures, and we've put some percentages by those, that they were determined by MALDITOF mass spectrometry, we see that there's some differences. And this is the way that the technique is often used. If you're producing a recombinant glycoprotein, releasing those oligosaccharides, you can compare one lot to another. If you are trying to produce a new glycoprotein, new recombinant, using different cell lines, using different cell conditions, you can look at those oligosaccharides after release with PNGase and see what changes have occurred. So in this case, we see that in sample B, the murine has peaks that they're labeled 5. It looked like they are highly sialylated, or maybe 2 sialic acids. The peak labeled 4 in the sample above is monosialylated. Well, it turns out because it's in mouse, it has more N-GNA or N-glycolyl neurominic acid, and that causes the elution to be a lot later. And we can see that when we treated the sample with neuraminidase to remove those peaks, and then we quantify the sialic acids were released. So let's look a little bit at that. In this case, we improved upon that separation. So if I go back to the previous slide, I'll note that the peaks that are between 10 and 20 minutes aren't fully resolved. There's some other peaks that are not separated in there. We can see that by the peak shape and the number of peaks there. But what we did about 4 years ago is publish some work where in this case, we've dropped the sodium hydroxide concentration to 50 millimolar in the separation, and we're resolving these peaks that I've labeled G0F, MAN5, G0, and I'm going to describe what they are in the next slide. We've been able to resolve those peaks, and specifically, if you look at peaks 4 and 5, is a compound called G1F, and I'm going to show you what those compounds are in the next slide. So if I look at G0F, what that means is it's a biantenary oligosaccharide. So it's got 2 branches, and it's got 0 galactose. So that's the G0. The F stands for the fucose at the core. So that's that little red diamond on the top right side of the structure. Now, if I look at the structure G1F, which is the second structure down there, that has 1 galactose, and that's denoted by the yellow circle. But in this case, that galactose could be on either of those antennas. So I'm showing it on the top antenna right now, but it can be in the bottom. And what we've done with the improvement in the separation conditions, what we've done is we've separated those 2 compounds now. Now, we see a lot of other structures here, too. G2F just means that it's both the galactoses. If the F is not there, that means there's no fucose on the core, and acetylglucosamine. So that structure, that red diamond that's on the top right corner, or the red triangle, excuse me, it's not a diamond, it's a triangle. So let's look at how do we prove we actually did that separation. So the bottom is the G0F standard. So that's, remember, no galactoses and 1 fucose. The sample before is our G1F standard before digestion. So the standard appears to have 2 peaks, one where the galactose is on the upper arm, another where the galactose is on the lower arm. If we treat with a galactosidase, not a calactosidase as I have here in my slide, but a galactosidase, that starts with a G, if we do that, we would expect that we would be able to get the G0F standard. And in fact, we get a peak after doing that treatment that elutes with the G0F standard. So the top trace shows that. We also shows that we either didn't completely digest or there's an impurity in our standard present, as there's still a small peak there at the position of the 1 isomer of the G1F. And what makes this powerful is I can look at both the starting material and I can look at the products. So I can look at the substrates, look at the products, and I can also look at the disappearance of substrates, so I can tell if my digestion is complete or not. And this has been used in a multitude of different ways with other enzymes, and I'm going to show you some of those in the next few slides. So in this case, let's take a look at human IgG N-linked oligosaccharides. This is some work we did earlier. And so we look at the bottom trace and that's trace number 1. That's the PNGase F digestion of human IgG. And we see we have a lot of structures in that 5 to 10 that 5 to 15 minute range, and those are all the neutral, the uncharged oligosaccharides. And then we see we have structures around 18 to 20 minutes, and those are our monosialylated oligosaccharides. So if we just run a sialic acid standard, the N-acetyl, the N-glycollyl, in this case we don't expect to see any N-glycollyl neurominic acid. We can see where that position is once we treat with the enzyme. So now we take the sample that's shown in trace 1, and we treat that with neuraminidase to release the sialic acid. So we can see in the top trace that all our peaks between 15-20 minutes have now disappeared because they all had sialic acid on, and now they're eluting together with the neutral structures. We also see a peak arise for the N-acetyl neurominic acid we released. So in this manner, we can tell what charged oligosaccharides, if they contain sialic acid or not. And if there were any peaks left over, we know they'd be charged, but they would contain some other charged component other than sialic acid. So that could be like a mannose-6-phosphate or galactose-3 sulfate or something like that. So let's look at another treatment. In this case, we've taken the sample. In this case, our PNGase F digestion of human IgG is in the top position, or 1. Let's just treat that with galactosidase. So we haven't treated with neuraminidase yet. We just treated with galactosidase. What we see, we greatly simplify the neutral region. So that region that was in the 10-minute region there, we see a lot of those structures, remember, have either 2 galactoses, terminal sugars, or 1 galactose. Well, since all the galactose is now gone, we've put that into that 1 major peak, but also shows us we have some other things there that don't terminate in galactose, or if they terminate in galactose, have some other thing, perhaps a bisecting N-acetylglucosamine. We also may have some high mannose structures which wouldn't be affected, like the MAN5, where we have 5 mannoses. We can also see that in our charge region, we've changed our distribution. So that means some of those charged oligosaccharides actually had a galactose at the terminus, which is what we'd expect. We'd expect to have a galactose. Some we might not expect to. We could just have an N-acetylglucosamine. But again, this allows us to identify certain structures. And finally, we can first treat with neuraminidase and then treat with galactosidase. And as we see, that greatly simplifies our final product there. We're getting mostly that G0F product, but we also would have some G0, which is probably the peak to the right of the larger peak. And then our sialic acid's also been released. That's why we see that doublet of 2 peaks there. And again, we've got better separation conditions now for these, so we'd see a little bit more resolution. But this work was done previously, and what this shows is the power of using enzymes and being able to see that substrates and products as well as disappearance of substrates in identifying structures. So one of the questions I often get is, how do you figure out how things elute? How do you rationalize a separation? A number of years back, almost 20 years ago, I put together 12 empirical rules that was published in Glycobiology as an open letter. And what it talked about is how you could rationalize separations on CarboPac columns. At the time, we just had the CarboPac PA1 and PA100, but these same rules apply to the CarboPac PA200 column. And then these are, as I say, empirical relationships, but because they've been taken from data that's been published in the literature and some of the things we've done in our group, our labs here at Thermo Fisher Scientific. So, as I mentioned, is one of the probably mentioned earlier, the larger an oligosaccharide is, the later it elutes. So if it has more exposed hydroxyl groups that can be ionized, it's going to bind to the tighter column tighter, and then require greater acetate, so it's going to elute later. So if we have a MAN5, which has 5 mannoses versus a MAN7, we'd expect that MAN7 to elute later, and in fact it does. Next thing is, since we're doing ion exchange, is not all that surprising, is we have increased charge, so increased sialation, increased phosphorylation, sulfation. We're going to get more retention, so those things are going to elute later. Now, the thing that's not very common that you wouldn't expect is if you add a fucose, so you're making the oligosaccharide larger because you're adding the sugar, you actually get less retention. So I didn't really point it out in those previous slides, but that G0F, so that no galactose in a fucose, that actually elutes before G0, where you don't have the fucose. So that makes it different from a lot of other techniques. So we'll remember that for some future discussion. We also have a situation, which I showed you before, where an oligosaccharide that has an alpha-2,3 linked sialic acid elutes later than the same oligosaccharide with an alpha-2,6. So remember when I described that Fetuin separation, that's exactly what we saw, and we can rationalize the full separation of Fetuin with that rule and a few other rules. So there are actually 8 more. I'm not going to go over those today, but just to give you an idea that separations do make sense, and you can rationalize them, especially with the use of enzymes to help you determine what is there. So I've been talking about N-linked oligosaccharides. I mentioned O-linked oligosaccharides. We also separate those. I'll show you a little bit of data on that in a bit. But let me go through polysialic acids. Polysialic acid is just sialic acids linked together in a long polymer. In this case, we can separate these. We can see up to degree of polymerization up to like 80 to 100. So there'd be 80 to 100 sialic acids in a row. A lot of our customers have done this separation. In this case, we're using a curved separation to get more peaks. What I want to point out is, because those are highly charged, we can actually use, and our customers have shown this, we can use nitrate instead of acetate. And that actually allows us to elute more polymers. In this case, this is application note 1013, and you can see that work there. But again, in this case, we're using nitrate as an eluent, which is, for highly charged things, is something we can do. So I often get asked about, what about the electrochemical response? Are they equivalent for every compound? Well, they're not, but they're very closely related, as we'll see. If we look at the next 2 slides, I'm going to have 10 structures. These are all from bovine Fetuin. A couple of these are the structures we looked at before in the separation. But the ones with these diamonds with 3, there are 3 sialic acids, so we have a lot of trisialylated structures. And we also have some tetrasialylated structures, some disialylated. Here's some other structures. We even have pentasialylated structures. So if we take a look at these 10 structures, this is a publication, as I'll cite in the next slide here. What they did was looked at the response of those structures versus glucose. So here we look at versus glucose, and we see most of them are around this 4 times glucose response. So certainly these are bigger, they're responding more in glucose. But this family of oligosaccharides, all from the same glycoprotein, basically has a pretty equivalent response. The response for these, I think, was 4.2 plus or minus 14%. So that's the kind of range. Now, these experiments are pretty hard to do. You've got to know that you have the exact amount of glucose you think you have. You also have to have a pure oligosaccharide. You have to know how much of that oligosaccharide is there. You've quantified that probably by monosaccharide analysis. So there's a lot of error involved in even doing this experiment. Each of these have been injected a couple times. Now, we could also look at O-linked oligosaccharides. There's another publication that did that. These are some of the structures that were looked at in that publication. And in this case, they based the response as 1 based on structure B. And let me go back a slide here. And structure B is this structure here. We have a sialic acid linked to an N-acetylgalactosamine structure. So again, this is 1. The highest we have is 1.6. The lowest we have is probably about 0.7 here. Again, there's a wide range of structures, but a pretty close range of response, a less than 2-fold difference in the response. And this is the publication that data came from. I have a lot more in this area in technical note 133. So what about if you want to purify oligosaccharides or interface our separation to a mass spectrometer? So as I mentioned earlier, we do have preparative columns where you can purify the oligosaccharides and then you could dialyze. But we also have an online device called the Carbohydrate membrane desalter. In this case, this device basically removes that sodium hydroxide and sodium acetate and makes them water and weak acetic acid. So it gets we use, I'll describe this device in the next slide, but basically get our oligosaccharides into a weak acetic acid solution, which can then be dried. So no dialysis is required. Let's look at that device. So our sample here, the top we see it's in sodium acetate and sodium hydroxide. We've got, just say 3 oligosaccharides. They're labeled O1, O2, and O3. They go through our CarboPac column. They go through our detector. Remember, we need that hydroxide there for detection. And then we go into this carbohydrate membrane desalter. This device is based on our suppression technology from ion chromatography. We add an acid regenerant across a membrane, and what that does is it exchanges the hydronium, the sodium ion with hydronium, so we end up having oligosaccharides with a hydronium rather than a sodium, and we end up with weak acetic acid and water. Now we can actually use the same device and put it on, we can use a smaller device than this and a 2-millimeter device suppressor and put it right online to a mass spectrometer. Obviously, we don't want to put sodium hydroxide in a mass spectrometer, but weak acetic acid is okay. But we can also use this offline to prepare samples, which we could then be used for MALDITOF, used for electrospray by infusion, or used for NMR, for instance. So let's briefly compare HPA-PAD to other techniques. If we compare it to MALDITOF, there's actually 4 publications that I'm aware of that I've cited here that compared HPA-PAD directly to MALDITOF. And you see what the first one up there from 1996 says, that when they quantified oligosaccharides with both techniques, they got similar values. So the electrochemical response and ionizing a carbohydrate is much different. It turns out that they end up yielding a very similar response, and that's exactly what the other three papers said. Even most recently, this paper by Gray, and this is another paper that used low concentrations of hydroxide to separate those higG oligosaccharides. They also found that both had similar response. Now, what was pointed out in at least one of the papers that what HPA-PAD could do is that it could separate isomers. Now, I've shown you isomer separations, and you really, because isomers are isobaric, you don't get that information from the mass spectrometer in this case, because you're not getting any kind of cleavages. So in this case, we're getting a little bit more information from the HPA-PAD, but essentially they're yielding the same response. Now, if we compare HPA-PAD to helic chromatography with fluorescence detection, or capillary electrophoresis with laser-induced fluorescence. What we see here, what I've said here is that HPA-PAD is very orthogonal to CE. Basically, what things elute early by CE, elute late by HPA-PAD. So as Elizabeth Higgins has said in her review, really for oligosaccharide analysis from glycoproteins, you really need 2 techniques, whatever those 2 are. So HPA-PAD and CE could obviously be those 2 techniques. HPA-PAD does have some orthogonality to the helic method. Mostly it's due to that fucose difference I showed you, where the fucose causes the oligosaccharide to elute earlier in HPA-PAD. I say the working sensitivity is similar. Certainly fluorescence is a bit more sensitive than PAD, but usually you require a certain amount of sample to work up that fluorescence sample so you can do number of injections. With PAD, we can literally inject everything we have, so that's what I refer to as working sensitivity. Again, HPA-PAD requires no derivatization. It may require a little bit more time per analysis currently with some of the separations we have, but again, you're not spending any time doing any derivatization. We have better separations of charged oligosaccharides, especially compared to CE. And because we're not doing any kind of derivatization in acidic media, we are able to preserve our sialic acids. So we have the best way to see sialation. And this slide, I'm getting here near the end here, and this slide shows all the other kinds of sugar analysis that can be done by HPA-PAD. I've mentioned a lot of these before. I haven't talked about sugar alcohols. We also do small polysaccharides that are just linear polysaccharides, sulfated sugars, some synthetic sugars, fluorodeoxyglucose, one of the things that it's done by one of the USP methods. And we've also can analyze carbohydrates from a wide variety of samples. I've been talking about glycoproteins today. We could also do it from glycopeptides or glycolipids once we release the sugar. And you can read through all these in fermentation broth, specifically in biopharmaceutical analysis. We can look at the sugar content of our broth. And as you can see, there's a number of other things, including vaccines and the sugars that we might use in pharmaceutical preparations. So finally, I'd like to just conclude with three statements here. Hopefully I've shown you that we get high resolution of separations from N-linked oligosaccharides. I didn't show you specifically O-linked oligosaccharides, but a couple of the papers I referenced do show that. So it's one technique that can be used for both because we don't have any derivatization. And as I mentioned, besides being able to do both types of oligosaccharides, we can also use monosaccharides, sialic acid, sugar phosphates, and a wide variety of other carbohydrates I showed you in the previous couple slides back, And then finally, we can use HPAE-PAD to prepare samples of pure oligosaccharides, either semi-preparative column or for NMR, for mass spec. And we can, with a 2-millimeter suppression device, actually directly connect it to a mass spectrometer. And this gives you a little bit different selectivity than some of the other techniques that are used. And with that, I'd like to thank you for your attention today, and I'd be willing to accept any questions you may have.
Thanks, Jeff, for that comprehensive presentation. If you have any questions that Jeff hasn't answered already, please submit them now. Before we start the live Q&A, I also want to let you know that a post-webinar survey will deploy shortly in the presentation manager. You might need to disable your pop-up blockers in order to see it, but please do and take a few minutes to respond. Your comments are extremely valuable to us. All right, let's start our Q&A discussion. We have a lot of good questions already, and we'll answer as many as we can.
Okay, Jeff, our first question is a quick one. Can you use water instead of acid for the membrane desalter?
Well, that's a good question. You could use water, but it would probably not be very effective. It's an electrolytic device, so it is creating hydronium ions or protons to exchange with the sodium that is in the eluent or the mobile phase. But there's not enough of the hydronium ion created to fully exchange with all the sodium. So that's why we add acid, too, to assist that process. So maybe if the eluent was weak enough, meaning there wasn't so much sodium, you could do that, but generally that's ineffective, and that's why we use acid also.
Okay. Is there any solid phase cleanup system to remove sodium hydroxide from the eluated samples?
Yeah, so when the samples are eluted, they're either in sodium hydroxide or sodium hydroxide and sodium acetate. So for oligosaccharides, we're talking about sodium hydroxide and sodium acetate. We could use a cation exchange resin in the hydronium form to exchange out the sodium. So that would make the sodium hydroxide water, but it would make the sodium acetate weak acetic acid. In that case, we'd probably dry the sample to remove that. And when we have the weak acetic acid there, if we sat that long enough, if we had sialic acid present in our oligosaccharides, we'd lose some of that. So we'd have to get that dried quickly. You could do the same thing by dialysis, too, and that's what we've done in the past.
Okay. Did you have any cleanup step after the galactosidase treatment?
I'm not sure exactly in that experiment if we did. My belief is, and generally we do not have to, and the reason is that the galactosidase digest is in something like a citrate buffer. It depends on the concentration and how much we're going to inject. The only thing we might do is dilute the sample. We don't want the amount of citrate, which is an anion, overloading the column. Generally, we have more than enough capacity on the column, so we don't have to do that. It's possible we did some dilution. just to inject the amount we wanted to, but I would say probably not. The only other way that I would consider doing a sample prep is if after doing the digestion I noticed that there was visible particles or precipitate, then I would filter the solution. But generally we don't see that. So generally we just inject it or perhaps dilute and inject it.
Okay, I have a two-part question now. What other types of compounds are electrochemically active, organic acids, amino acids, etc., and can we still use this type of system for separation and detection?
Yeah, so that's an excellent question. What I talked about today is using electrochemical detection with a gold electrode for carbohydrates, and certainly there's a variety of carbohydrates, as the one slide showed, that we can do that with. If we just had a gold electrode and then changed the column, there's a number of different other compounds we can detect, most notably amino acids, and then sulfur-containing compounds where the sulfur is not in a fully oxidized state, something like a thiol. Antibiotics often have sulfur in this state, so the system's been used for antibiotics, but anything that sulfur isn't fully oxidized. Now, if it's a sulfate, that's fully oxidized, and we wouldn't be able to detect that. Now, if we change the electrode, we have a couple different other working electrode options for that detector. We can have a glassy carbon electrode that's been used for compounds like catecholamines. We also have a silver electrode where we can detect things like iodide, bromide, a number of other compounds that are escaping my memory right now. And then we have a platinum electrode where we can do alcohols and glycols. Now, in those cases, we're going to obviously switch the column and generally switch the mobile phase, but that can all be done on the same chromatography system.
Okay. Does Triton X100 need to be removed prior to injection using the CarboPac 200 columns, for instance?
Yeah, I guess that's a yes and no question or answer. Generally, Triton is detected, so it's got hydroxyl groups. They are oxidized. The Triton 100 will elute in the void volume. What we try to do is minimize the amount there. And if we're looking at charged oligosaccharides, so sialylated oligosaccharides, they're going to elute well away from that. If we're looking at neutral oligosaccharides, it's possible that if we have too much there, it'll interfere. So in that case, we might remove it. I would refer anybody that's interested to our application update 176, where we talk about preparing PNGase F digests for HPAE-PAD, and that specifically discusses the Triton X100.
Okay, Jeff. Some oligosaccharides are negatively charged already. Do I still need to have sodium hydroxide in my mobile phase?
Again, that's probably another yes and no answer. We say yes because with the hydroxide present, then we are able to detect the oligosaccharide. Remember that our electrochemical detection has to be at high pH. That said, we can separate those oligosaccharides just with sodium acetate. Now, to detect them, then we would have to add some hydroxide after the column, so post-column before the detector. In fact, I think it's almost 20 years ago, scientists at Amgen showed that you can get some different selectivity when you separate sialylated oligosaccharides, N-linked sialylated oligosaccharides with no hydroxide in the mobile phase, and then adding the hydroxide afterwards for the detection.
All right, now I have a question that is not a yes and no question. Why do you need a metal-free system to do HPAE-PAD?
Well, you could probably not use a metal-free system for maybe a couple weeks, a month, and have no problems. But generally, with a stainless steel system or even a titanium system, you don't want to be pumping strong sodium hydroxide through that system. What's going to happen is eventually you're going to release metals. Those metals will first contaminate the column, and that's going to change your separation properties. It's also going to void your warranty. We don't say that these columns can be run on metal-containing systems. And then it's also going to get on your detector working electrode and change the properties of that gold working electrode, because now it's going to become a gold and some other metal. So it's not a good long-term, for good long-term success, we certainly don't recommend it.
Okay, unfortunately our time is up. Thanks for listening in, and thanks for the great questions. This webinar will be archived for 6 months on our website, www.genengnews.com. If you missed parts of it, you can watch it again, or you can recommend it to friends and colleagues. I also want to thank Jeff. Thanks for answering so many questions, as well as our sponsor, Thermo Scientific.
Thank you.